deals with the breakdown of periodic table. So some of the stuff we've already mentioned or already worked on. It's working, yep, okay. Second half is, it works with these charts. Now, I'm going to treat this chapter like I've done in the past. We're going to cover this entire chapter in the next few weeks. Going to ramrod through it. Whatever's on this particular chapter will be on the midterm test. We will not have a separate chapter test over 6. So we're going to include this chapter in the exam that you will be taking. You guys take this on Tuesday, the 17th.
7/126.
Yeah. And then that way, when we get back from break, we start hitting chapters 8 and 9 and continue through. So just keep that in mind. It will not be a separate test over chapter 6. All right. So this, as I said, this is not complex, the first half. The second half, as you can see with this chart, is going to be a little bit more involved with those. Okay, so let's begin. Here is the man we'll start with, Dmitry Mendeleev, who is basically considered to be a father of the periodic table. He was a Russian chemist. What happened in the 1860s, actually pretty much during the Civil War here in America, all the chemists around the world, all the international chemists, realized they were kind of hamstrung because everyone in every country had their own determination of what mass of elements were. And so France would do their experimentation based on their definition of mass of an element. America would do their own, England would do their own, maybe over in China would do their own, and so on, so that when they collaborated and they tried to find out what are you guys doing in France, chemists here in America, they couldn't repeat necessarily everything because they're using different standards of mass. So they realized that we're going to have a Congress of chemists. We're going to have to get together internationally and decide some things so that we can collaborate and chemistry can move on to better, bigger things. So they did. They met over in Europe. Dmitry Mendeleev didn't make the trip. One of the reasons he didn't make it is he couldn't afford to make it. But a lot of chemists around the world did. And when they met, among many things, they decided that this first international Congress of Chemists they came up with a standard mass. Now the standard mass that we're looking at was the atomic mass unit. And so on our periodic chart now we have those red numbers, those atomic masses that they decided on. Now all of them weren't done. I mean, there are a lot of elements yet to be discovered, but the ones they knew about, they determined what the mass would be for those, relative mass would be for those elements, and then things could progress. Well, that information from that Congress got to Dmitry Mendeleev, and he noticed something. He noticed a connection between atomic mass and properties of elements. He noticed there was a connection. And so what he did was basically on these pieces of paper, he would write the element with the atomic masses and put them in increasing atomic mass order. All the ones that they knew. In fact, there was a whole group of elements they didn't know about. They didn't even know they existed. But the ones that they knew, he put them in order, increasing atomic mass order. And he noticed something. He noticed that every so often there was a repetition of properties. So what he did was he put those elements that had similar properties in rows. The ones that had similar properties. All right? So this is a kind of, it's kind of different arrangement. But this is for your listening and enjoyment. There's a dancing Mendeleev. No one knew historically. Mendeleev was a very good dancer. anyhow, this is kind of what his chart was like, all right? You can see that there's a lot of gaps in it, all right? A lot of question marks and so on. But if you notice, this is kind of grouped a little bit different than he did. These are arranged by column, but his was in rows. So really, this would have been turned on its side. And when he put them by increasing atomic mass order, he noticed that there was a repetition of properties. Now, he noticed, for instance, for this one, like potassium and calcium, and then the next one they knew about was titanium. But titanium looked more like these elements than these elements. So he surmised that there must be a missing element there. And so these question marks are where he perceived that there were elements yet to be discovered that fit in them. So let's talk about mental waves. What is the difference between his table and the modern periodic table? His rows are columns in today's table, and of course, his columns are rows in today's table. So it's like if we took that periodic table and turned it 90 degrees, that would be kind of what his table would be like. But he did notice that in his periodic table, pretty primitive periodic table, there was a whole group of elements that must be missing. Does anyone have any idea what group of elements might be missing on the periodic table?
Gases.
Which gases?
The ones in green.
Yeah, the last column. Those are called the inert or noble gases. Those are gases that do not need to react. They already have a filled outer shell. So it's very hard to discover because they're unreactive. We could discover a lot of the other elements because they can react with other elements. And we could test them out experimentally, and it's very easy to discover properties of elements because they react with other elements. But this whole group, the noble gases, don't react. So they were completely missing from his chart. In fact, we did discover the first noble gas on this planet. We discovered it in the sun. So it was so hard to discover their reactivity, because they don't react, that they had to go off planet. They had to actually go to our sun to discover at least the first, which was helium, the first noble gas. There are also gaps in this table, which I alluded to. He put them in increasing atomic order. He reasoned, and correctly reasoned, that, this, if I keep them in order, then this next element doesn't belong with these other elements. It belongs over in the next group. So there must be one that's missing. And he was so good at what he did that he could predict properties of that missing element, even though it had not been discovered yet. And he was real close to the properties he perceived that element would have. And the other thing that's different is this table was arranged by increasing atomic mass. Our table today is ordered by increasing atomic number. Well, doesn't it make a difference? If you have an increasing atomic mass, when you have an increasing atomic number. Well, if you look at the table, all right, and if you have your tables, you can look at it. I want you to look at cobalt and nickel. Let me see if I can get that pointed. All right, I think it's right here. These two. What's the cobalt's atomic mass? What is nickel's? Which one's bigger? See, 58.9. Yeah, cobalt's bigger, right? So if you did it by increasing atomic mass, wouldn't cobalt be placed after nickel? All right. Another one is tellurium and iodine, which has a bigger mass. tellurium should be put in Mendeleev's table, tellurium should be put after iodine. At least Mendeleev had the foresight to know that cobalt and nickel should be placed in the order. He couldn't understand why, though. He didn't understand why nickel should be placed after cobalt, considering nickel has a mass less than cobalt. But at least he knew, according to the property, it should be placed after. So what are some differences? Rows and columns are different. He had gaps. He had a whole group of noble gases that were not part of this. And he had his by increasing atomic mass, not by increasing atomic number like our table today. All right. So, what we're talking about with Mendeleev and why he did it the way he did is because of the periodic law. And the periodic law basically says that when the elements are put in order of increasing an atomic number, there is a repetition of properties. A repetition of properties. Now, what does that mean? Well, if we were to go to lithium, which is row 2, all right, increasing atomic number, increasing atomic number, increasing. The next element after this would be sodium. But sodium has a property like hydrogen. Okay, so we're going to put sodium, here's a property, lithium, sodium have similar properties, potassium, sodium, lithium have similar properties. So if I keep on putting them in order, increasing atomic number, there is going to be a repetition of properties. Every so many elements, there's going to be a repetition of properties. That is what the periodic law is all about. Now, let's define some things in the periodic law. This is something you may have already covered, so we can get through it pretty well. What do we call columns? We call columns groups or families. Columns are groups or families. So if we count over here in the periodic chart, we have then 18 groups or families as you number them across. There's 18 columns across the periodic table. So each column is a group or a family of elements. What about rows? Rows are called periods. Rows are called periods, periodic table. So far, how many periods are there on the periodic table? 7, right? Because these down here actually belong in the gap here. So there are 7 periods. There's 18 groups or families. There's 7 periods in all. What else do we have? Well, we have groupings, blocks or so on. We have what's called the main group elements, or called representative elements. I've already alluded to this in the previous chapter. So which ones are we talking about? We're talking about the 1A through 8A, or the groups 1, 2, 13 through 18. So the main group elements are the first 2 columns, all right, and the last 6. Now these are called groups 1 and 2 by this vernacular, going from 1 through 18. These are groups 1 and 2, and starting here, 13 through 18. All right, or if we use the Roman numeral, it'd be 1A and 2A. Then we skip over to 3A through 8A, depending on which label you want to use for the groups or families. Do you use the 1 through 18 or the Roman numeral kind? So first 2 columns, the last 6. We call that the S block and the P block. Those are the main group or representative elements. All right, now let's go on.